Hi class, this is a lecture on confidence intervals as they relate to proportions. And now this is an application of the central limit theorem, which I've talked about a bunch in class. But in this video, I will actually just spend my majority of the time talking about the formula and crunching through some examples for you. All right, so let's go over some concepts of estimation again. So the objective of estimation is to estimate the unknown value of a population parameter, like mu, like the population mean mu, or p, the population proportion, right? And this is done on the basis of a sample statistic calculated from sample data. So like here's an example we'll work with first. Suppose WCC Student Affairs Office may want to estimate the proportion of students that want more campus weekend activities. So they don't know what percentage of people of students that would want this. So they'd have to estimate. So there's two ways you could do this. You could do it with the point estimate, which we've talked about in class. That's just a single value estimate. Or you can do it with the interval estimate, like a range estimate. All right, so the point estimate for P, the population proportion, if you remember, is just called P hat. And all that is X divided by N, like this. And this is the sample proportion of X successes in a sample size of N. And this is the best best single value estimate for an unknown value of the population proportion P. So if you don't know what P is, you just take the sample proportion, and that's a good way to estimate the real value. All right, but estimating the unknown population proportion here, let's stick with that example. So we want to estimate the proportion of students who want more weekend activities. So what they do is to say in a sample of 1,000 students, 590 say that yes, they want more weekend activities. Little typo here, but p hat here is equal to 590 divided by 1,000, which is 0.59. And this is that point estimate of the unknown population proportion p that want more weekend activities. But now here's the thing. Does exactly 59% of students want weekend activities, or is this just the value we get from talking to 1,000 students? Like, I don't think the real value is exactly 0.59. All right, so here are the shortcomings of that I was kind of hinting at. All right, p hat, which is 590 divided by 1,000.59, is the best estimate for the population proportion of p. But how good is this best estimate? Like, is it the real actual value? So there's no way to measure the reliability of this. There's no way to know, like, just the single value, how close it is to the real one, or just from looking at the single value, what is the real value? All right, so then we fix this by using another type of estimate, right? And this is what we call a confidence interval, an interval estimator, if you will. So a confidence interval is a range or an interval of values to estimate the unknown value of a population parameter. Right, so just like when we talked about in class when we had confidence intervals for a mean, right, we have a confidence interval for a population proportion of P. So this is a 1 minus alpha times 100% confidence interval for P. All right, well, just like we were talking about in class, you take the point estimate and you add and subtract what we call the margin of error. So you have what's called a lower bound and an upper bound when you do this. So the lower bound, you just take the point estimate P hat and you minus something. The upper bound, you take the point estimate p hat and you add something. Well, what it really is it's the critical value times the standard error. So the critical value is this z with the subscripted alpha divided by 2. And the best way to find the z critical value is to use this little chart I have over here. Like, we've done this a ton in class. If I want to find a 95% confidence interval, the critical value z of alpha divided by 2 is just 1.960. And then you have to multiply that by the square root of whatever p hat was times 1 minus p hat divided by the sample size. And it's the same thing down here. All right, now in some of my slides, you'll notice that I have p hat times q hat. And all I do is write q hat as 1 minus p hat instead of rewriting it. But all this is a basic formula to plug and chug through. All right, so let me give you an example. All right, so a voter preference poll typically samples, say, approximately 16,000 voters. All right, so let's just suppose that you wanted to estimate the proportion of people who support some new policy. And what they did was they found out that from talking to 16,000 voters that p hat was 0.52. So then if we desire what we call a 95% confidence interval for P, this is how we would calculate it. We would take P hat and we'd add and subtract the critical value, 1.96. Well, I want a 95% confidence interval, so it's just 1.96, times the square root of P hat, and remember 1 minus P hat I called Q hat, divided by N. So it's 0.52 plus or minus the critical value, all right, so 0.52 comes from the P hat, 1.96 times the square root of P hat, which is 0.52, times 1 minus P hat. So 1 minus 0.52 is 0.48 divided by 1600. So you have to take the square root of all of that. Now let me show you real quickly how to do this in your calculator, just so you can see exactly what I'm doing here. So I'm taking 1.96 times the square root, now in parentheses I put 0.52, times 0.48 divided by 1600. I close my parentheses, and that's how I get this small margin of error as 0.024. All right, well then all you're going to do is you're going to take 0.52 and subtract 0.024. That gets you the lower bound. And you're going to take 0.52 and you're going to add 0.024, and that gets you up the upper bound. So all we're saying here is, look, I am 95% confident that the real proportion of people who support this policy is somewhere between 0.496 and 0.544. That's all we're saying. All right, let's do another example real quick, right? And this is about medication side effects, all right? So arthritis is a painful chronic inflammation of the joints. So an experiment on the side effects of pain relievers examined arthritis patients to provide the proportions of patients who suffered from side effects. So people who were taking ibuprofen to deal with their arthritis, you know, what proportion of them might have experienced some of these side effects right here. All right, so here's what they did. 440 subjects with chronic arthritis were given ibuprofen for pain relief. And of those 440, all right, who were given ibuprofen for pain relief, we see that 23 subjects suffered from adverse side effects. All right, so let's calculate a 90% confidence interval for the population proportion P of arthritis patients who will suffer some adverse symptoms. All right, well, here the confidence interval is P hat plus or minus, I just call it in this slide here Z star for the critical value, times the square root of that P hat, Q hat, divided by N. All right, so first off, what is the sample proportion here? Well, we can just see that this P hat is the 23 people who suffered side effects divided by the 440 who took the ibuprofen total, and it turns out that roughly 0.052 here is the proportion, or roughly 5.2%. Okay, that's not too bad, I guess. All right, so for the 90th confidence level, the critical value is 1.645. Let me go back and show you where that comes from. I want a 90% confidence interval. That's 1.645 right there. So this now just becomes a plug and chug problem. So P hat plus or minus the critical value times the standard error. Well, P hat is 0.052 plus or minus the critical value, which is 1.645, times the square root of all of this. So it's P hat 0.052 times 1 minus P hat, or 0.01 minus 0.052. You have to close that parentheses there in your calculator. Divided by 440. All right, now let me show you how to get that, just so we're clear. And I'll go back to the slide so you can see it. I'm going to do this part right here. So 1.645 times the square root of 0.052 times, in parentheses, 1 minus 0.052. Close that parentheses, divided by 440, and then close the final parentheses. And you get this, I did it all in one step, 0.018. Here I took this 0.017 and I've just rounded it a little bit. the reason it gets rounded here again is just because of the compounded rounding. So then the 90% confidence interval for P is 0.052 plus or minus 0.018. So the lower bound is the subtraction part. So 0.052 minus 0.018 gets me 0.034. And 0.052 plus 0.018 gets me 0.070. So what we're saying here is that we're 90% confident that this interval here that I calculated right above contains the real true proportion of arthritis patients that will experience some adverse symptoms when they take ibuprofen. All right, let's talk about the impact of the sample size here. All right, suppose instead this is my original 90% confidence interval, but I only talked to 440 people. But if I talked instead to 1,000 people here, all right, what I notice here is that my confidence interval, look what happens to my margin of error. When I talked to 440 people, it was 0.018. But when I talk to 1,000 people, my margin of error goes to 0.007. So it looks like the interval gets smaller, right? So what happens here is when the sample size is increased, all right, what we're seeing here is that the 90% confidence interval is narrower. All right, so it's important with another thing here, the higher the level of confidence, the wider the interval will be. So if you have a 95% confidence interval, that'll be wider than a 90% confidence interval. And increasing the sample size n will make a confidence interval with the same confidence level. So notice back here that the p-hat didn't change. All right, it will make the confidence level narrow, i.e. I'm saying it'll be more precise.